Hello and welcome to our next discussion on estimating population variances and the distribution that it gives me as comparison distribution in the hypothesis testing procedure. One thing to note here is when the population variance is known, as was the case up to this point, the sample variance we calculate in this hopefully familiar to you formula. However, I don't know if my pen wants to work with me, but here we go. When the population variance is not known, which happens to be more often the case, we need to use our sample to estimate the population variance. Then it turns out that estimation needs to take the sum of the squares and divide it by n minus 1, where n is the sample size. For this to be what we call, not that it really matters, but just for the sake of being complete, an unbiased, that is ugly writing. Why is my writing so weird right now? Estimator. I think my pen is being super weird. We call an unbiased estimator. This, when I divide by n minus 1, is the correct estimation of the true population variance. Now, if you look at your formula sheet, then it's over here as well, the estimated population variance, where I use the n minus 1. We call that the degrees of freedom. Degrees of freedom, n minus 1. Because if I know n minus 1 things and the answer, then that one thing, last thing, I am not free to choose. Degrees of freedom will come up a little bit more in future sections. My laptop is very unhappy right now. It doesn't like this new formula at all. However, it has to. Let's not even see that top one anymore. So for example, if I have five participants here, they have some scores. I calculate the sum of the squares in the same way, but to estimate the population variance, I divide by n minus 1, so 4 in this case, and then I use that in my standard error and comparison distribution and whatnot. The distribution that I'll use in the hypothesis testing procedure is not a normal distribution for small samples. It follows what is called a t-distribution. So as the sample size, which is of course the degrees of freedom is the sample size minus 1, as the sample size, when it is small, this distribution resembles a normal distribution, but the tail is bigger. And then as the sample size, the degrees of freedom increase to like past 100, they are extremely close to each other. And when you look at the statistical tables that I'll bring up here, we will then use the t-distribution tables. Now, because there's technically the previous tables for each degree of freedom, they just give us the highlights. For different degrees of freedom, I have the familiar alpha values, and they only focus on those. So they're not as detailed as before, but we don't need them to be either. And then it stops at 100, past 100. These values are identical to the normal distribution table. But let's do an example and see what this looks like. So here we have an example where we are investigating. Can I zoom in? Don't know if I can. It's not bad. It's not bad. I think I'm gonna try it. Where we are asking, let's suppose you live in a certain dorm. You want to know, is the total number of hours studied more in my dorm versus students at the college in general? That's my question. So then population 2 is all the students at the college, and we are given that the mean hours studied is 17. We don't know the variance. The distribution is normal. We need that because we don't have a large sample. Then we take a sample of students living in our dorm. We get a sample mean of 21, and the sum of the squares as part of the calculation being done for you is that 694. And our hypothesis testing question can be phrased by way of the null hypothesis that, well, let me rephrase it this way. What do we want? Ideally, we want to see if the mean hours studied in our dorm is more, where's my cursor? Cursor disappeared. Oh, that's nice. Is more than the college mean. And then the null hypothesis that it isn't. So before we can continue, I apparently lost. Oh, there's a cursor there. Oh, okay, never mind. I can't write, but things are falling apart. That's not something you need to worry about. We'll keep going. I need to first estimate the population variance. Okay, I'm just going to do it with the mouse because I just want to scroll. There we go. And we'll skip on drawing anything too fancy. We have to calculate the population variance estimate. So the only thing to really remember that sets this apart from the hypothesis testing procedure we've done previously is that I'm dividing by n minus 1, so 15. And we get a variance of 46.27. That is the variance that I'm using in my comparison distribution, where the variance of the distribution of means is still the standard error using dividing by the sample size n. That doesn't change. Nothing here changes, only the estimated population variance. So I get my comparison distribution is still the distribution of means. The mean of the comparison distribution is the same as the population 2 mean, 17, that I'm testing against. I now get my standard error, 1.7. And in this case, the distribution is a t-distribution because we had to estimate the variance by way of the sample. Okay. Then we are going to choose an alpha, let's say 5%. It's one-tailed. We want to see if it's more, if students at our dorm studies more. We have our degrees of freedom. We go look in our table. So we're looking at a 5% alpha. Let's see if I can just zoom in on that a little bit. It's a one-tailed test, 5% alpha, 15 degrees of freedom over here. 1.753. 1.753. 1.753. There we go. Then let's visualize what is happening instead before we reveal too much. We have our population. We have our comparison distribution, which is now a t-distribution. We have our cutoff according to the alpha of 5%. We looked it up. And then we want to see where does our sample sit. Now, of course, you can do that by way of the raw scores or the z-scores. That's totally up to you. In this case, we convert the sample mean, which up here is 21. That's what happened from the sample at our dorm, average of 21 hours studied. I'm guessing in a week. We convert that to not a z-score, but a t-score in the exact same way. Sample mean minus population mean over standard error, which is really the approximation of the standard error, which is why we use an S and not a sigma. Plug that in, get that our observed t-score is 2.35. Well, the cutoff was 1.753. Now, the nice thing is here, you can still think the same way as you did previously. Still think bell curve, everything is the same. Our sample puts us way further than the cutoff, and we therefore reject the null hypothesis because our observed score is more extreme than the cutoff. Reject. Research hypothesis is supported. The evidence does support the hypothesis that students in our dorm study more than at the college in general. So everything is very similar. Focus on the one difference, which is over here. We now have to estimate the population variance, and we divide by n-1 to do that. That's the picture. Think of the picture. Visualize. Everything is very similar. So let me just see if I can zoom in a touch here. Oopsie. Does that still fit? Ooh, it's very close. So the hypothesis testing procedure, when compared to the previous situation, the z-test, if you will, this is now a t-test for a single sample. T-test for a single sample. What's the same? What's different? Everything fits. Okay. Hypothesis testing setup is the same. Research hypothesis, null hypothesis. About the populations, no difference. Population mean, no difference. Population variance, yes, I do now estimate that from the sample. Difference over there. Standard deviation, no difference. Take it from my estimated variance. Shape of the comparison distribution, yeah, different. It's now called a t-distribution. Degrees of freedom, sample size -1. I therefore use a t-table to look up the cutoff, the t-scores. And there's no difference in how I make that decision. I just use the t-distribution, t-table, and call it a t-score. No difference in how I make the decision or the conclusion at the end of the hypothesis testing procedure. So a lot of similarities. It shouldn't be overwhelming or difficult. When there's a couple of differences. The main difference is we have to estimate the population variance by way of the sample, and then it's the t distribution table score instead of the z distribution table score. Okay, let's wrap this up with one more example where we are seeing two students taking psychological statistics differ from a mean of 4 on the question, to what extent are you a morning person? We want to see, is it different than the general average of 4? So my population 2, can I zoom in on this? That's a little big. Yeah, not going to. My population 2 is sort of my reference general baseline with a mean of 4. And I want to see in the statistics class, is it different from 4? I don't know. Is it up or down? So this is going to be a two-tailed test. We do some calculations. Our sample is 105 students. Do the calculations. In the normal questions, this will be given to you in some sense, at least the sum of the squares. We get a sample mean of 3.46. Sum of the squares is used to estimate the population variance. Sum of the squares divided by n minus 1, so 104. We get 310. Distribution of means is our comparison distribution. I would write comparison distribution here, but my pen doesn't want to write. But we don't really need it. It's okay. Maybe in the next video. The pen is going on strike today. Our comparison distribution is the distribution of means. Still didn't change. We're using the estimated. I'm going to zoom in on that, like so. Estimated variance, still dividing by n. Standard error. We now have a t-distribution, and the degrees of freedom is important for the t-table if I ever need to look something up. Okay, so now let me just position these things without revealing too much. We are going to see, where is our cutoff? Let's go with a 5% alpha. Again, it's two-tailed now. I really wish I could draw this, but it's okay. We'll picture a two-tailed test, a distribution up here. There we go, two-tailed, there it is. If we have 5% alpha, that means 2.5% in each tail, but it's already done for us in this table. 5% is already giving us the correct cutoff, of course, plus and minus that number. So you don't have to do anything. It's already split up for you and everything. So it's very convenient, this table. We see our cutoff with degrees of freedom 104. I go all the way down. Now I can't see it unless I zoom out a touch. Degrees of freedom over here. This is the column we're looking at. Degrees of freedom 104, 104. This table stops at 100. And after 100, the t-distribution and the normal distribution are so close together, there's virtually no difference between them, and we just have one row rather, for any degrees of freedom above 100. And we use this 1.96. 1.984. Oh, that is not right. That is not right. Why do you do that? It's right there. Well, that's unfortunate. It should be this 1.96. 1.984 is for 100. We are above 100. So we're at 1.96. That's a correction that I'm going to try and write with my mouse, but that's going to be a mess. 6. There we go. If you look at this versus what happened in the usual normal distribution case, where we were looking for the tail, we would be looking for 2.5% in the tail. We're going to have to go up another one, 2.5% in the tail. It's over here. You see it's 1.96. So past 100, the t-distribution and the normal distribution are the same for a large enough sample size. I go back to the t-distribution, not that we need to. One more. Laptop is just a little angry if I do too much all at once. So we're down here, over there. Now, of course, the slides here use a different number, but everything is the same after that. So please do make the correction. Where's my mouse? There's my mouse. So our mean score for the sample was 3.46. Calculate the corresponding t-score and see how that compares with the cutoff line. And then we see, ooh, this is way further. And we therefore reject the null hypothesis. The evidence suggests or supports the hypothesis that students in this class are less likely to be morning people. Well, we can't really say that. We can only say are different in their morning person rating. That's all the hypothesis we're testing. Is it different or is it the same? You can set this up then and rephrase this to be a strictly less than. You'd have to do everything again, because with the same alpha all in one on one side in the lower end, it could change the strength of the sample and the evidence. Okay, so just watch your phrasing at the end here. Wouldn't say less likely. They're just different than the general assessment of being a morning person. All right. So again, thinking of, where's my picture? The nice picture I had for the previous example, where it still looks like a bell curve and everything. It is not technically for small samples. It has a slightly different shape in the tail, but the steps I use and the logic behind it is pretty much the same as what we're used to. So this is for a t-sample, a t-distribution. Let's go back to that table here. Also known as a t-test for a single sample. T-test for a single sample. Whenever I need to estimate the variance. All right, that'll be the end of this video. Until next time, where we will expand on this t-test to look at some variations that are not covered by this exactly. Until then.